Okay. So I'll be talking about my research area, and I will not exactly go into the deep into my research area, but I will give you some aspects which you can appreciate. And most importantly, this area is a span of many interdisciplinary fields. It will touch upon biology. It will touch upon different areas of science also, and engineering field also. So I will give you a talk about dynamical system perspective of natural events. So whatever natural events happen, it's a dynamical system. Okay. So what is a dynamical system and all we will see after this slide. So this is the outline of my talk. Like we will learn what is a dynamical system. Okay. Why we call it a dynamical system and how dynamical systems and nature are interrelated. What are fractals? Okay. Mostly you might learn this in your computational science course. Those who are in DSCS might be. And what is chaos theory? What is chaos theory? How many of you have heard about butterfly effect? Oh wow. Last year many were not knowing about this. But I can someone explain what is a butterfly effect? Yes, exactly. So a small change in initial conditions can result in a huge difference in outcome. In other way, it can mean that a butterfly wing in I think Texas can cause a huge flood or tsunami in Brazil, something like that. So a small flap in the butterfly wings can cause something huge. So that is known as a butterfly effect. You can also watch the Hollywood movie based on it. Okay. So we will watch a few of video illustrations also. Wow, what is dynamical systems and how it occurs in real life. Okay, so dynamical systems are systems evolving with time according to a given set of rule or rules. Okay. So can you give me, based on this statement, can you give me some example of dynamical system? So dynamical systems are systems evolving with time. Yes. So what is the best example you can give as a dynamical system? Programming languages? How? Yes. Like around 7, 8 years before it was Java dominating. Now it is Python dominating. Okay. So yes, that's a good idea. Any other ideas? Hmm? Yeah. I'm hearing sounds, but I'm not hearing the proper one. How about life? Life is a dynamical system. Life evolves, right? Life evolves. Life is not the same it was last year. Life continuously evolves. So every day is a new day, right? Every day is a new day, and life is a dynamical system. Yes, life is a dynamical system. Any other examples of dynamical system? Yes, human evolution is a dynamical system. Your money in your bank account is a dynamical system because it keeps on fluctuating, right? It keeps on fluctuating. Sometimes it is very low, sometimes it's very high, right? And sometimes it stays in the middle zone. Okay, you are neither too happy, you are neither sad. Okay, fine. Any other example of dynamical system which you are missing? Gadgets? How? How gadgets? Gadgets are also evolving. Yes. I mean, previously computers were this big. Now you can see the laptops also. Fine. Any sound wave? Yes. Anything with time is a dynamical system. Car models. Yes, exactly. Yeah. Another example can be weather. Weather is a dynamical system. For this related people, I can suggest weather. So, can you predict weather 15 days in advance with 100% accuracy? You cannot predict. I mean, okay, let me start with a motivation to you that can you draw a 3 centimeter line segment? How? Take a scale, put one line and put 3 centimeter line, right? But is it 3 centimeter? Is it 3 centimeter? There is an error. It can be 2.999, but it won't be exactly 3. It can never be exactly 3. There will be always an error. Whatever you do, whatever calculations you do, however machine learning comes, however AI comes, how much level they come, no one can eliminate error in this world. No one can eliminate. See, you could not eliminate error in your small scale with just drawing 3 centimeter or 1 centimeter. So my idea is, due to that tiny error, there will be a huge change in your outcomes. So therefore, when you go on to predict weather using all AI models and all, you cannot actually predict weather to the highest degree of accuracy, because a tiny change in your decimal point in temperature or humidity can fluctuate your future outcomes. Okay, so this is not me. This is a story of a real scientist, Edward Lawrence. We will, I think, if possible, we will discuss about him. So there are two types of dynamical systems actually: continuous dynamical systems and discrete dynamical systems. Okay, so what is a continuous dynamical systems? Like the weather you can model with differential equations. How humidity changes with respect to time, how temperature changes with respect to time. Yes, so due to that variation, you can predict whether rain is going to happen or not. Yes. So usually those are modeled with respect to differential equations or system of differential equations. Okay. The best example is a pendulum. I hope how many of you remember this equation? I don't want to force anyone, but this is a well-known equation in your class 12 physics at least. Sorry, it's pendulum equation, right? d2 theta by dt2 is just like an acceleration. Yes, fine. Okay. So this is just a dynamical system. Pendulum is also a dynamical system because it changes its position with respect to time. Yes. Now there is another class of dynamical systems known as discrete dynamical systems, which are modeled using discrete maps. Okay, that is xn plus 1 is equal to f of xn. So what is xn plus 1? That is the future. What is xn? It is the past. So you're kind of predicting the future based on the past. Okay, you are finding what is xn plus 1 depending on the previous state, that is xn. And what is the rule here? The rule is f. The rule is F. Remember my first line of definition, dynamical system. Dynamical system are systems evolving with time according to a given set of rules. So here F is a rule. So you take the past state, apply the F function, and it will tell you where to go to the next. Right? You are understanding? Can you give me a real life example of this? Discrete time dynamical system. Actually, we are living in a discrete time dynamical system, to be honest. Our life is actually a discrete time dynamical system. Okay. Does your age evolve continuously? No. Our age is evolving discretely. After 1 year, we transform, we increase our age by 1. Yes. It is not like your motorcycle speed, like velocity. Okay. That is continuous. Okay. You got the idea? Basic idea? Fine. Okay. So we have a point, we have some value, we apply the rule F, we go to the next point. That is the idea. Then we apply F again, we go to the next point. Next point, next point. So like that happens in your bank account. Like, yes, suppose in SBI you have deposited some account, some money in your bank account. You get, yes, if you do FD, fixed deposit, then bank gives you some amount, right? Because it gets profit from it. Yes. So every year it gives you some amount of money back, depending on your initial money. If you deposit some lakhs of money, then you will get a good interest. If you deposit some thousand of money, then you will get less value. Yes. So in finance sector, discrete dynamical system holds much importance. Anyway, so one best example is this logistic equation, which usually models biological scenarios. So those who are from ecology or bio AI, they might have known about this. Okay, this is known as something known as logistic equation. Okay, so Robert May, those who know, he's a biologist who models population dynamics. I mean, why not in the wild? Why not in the wild? Lion eats the deer, right? Lion eats the deer. So there should not be any deer. Why there is deer still? That's my question. Why not lion population has increased up to an extent that they can kill humans and they can take over the world? Why there is a balance? Where the balance is coming from? This is a good question to ask, right? I mean, lions, if a lion comes here, what happens? Everyone will run, right? So we fear the creature, right? So they are dominating creatures than us. But they fear us, but they are dominating. If possible, they can attack, right? So technically, they should evolve. The stronger the one is, the better they evolve, right? So why not lion has taken over the whole world? Why humans are still existing? Or why even, okay, human is very big thing to ask. Why deers are still existing? Why even birds are still existing? Eagles could have attacked the pigeons. Pigeons are the simplest creatures I have seen so far in my life. Okay. And so why not eagles are attacking the pigeons and pigeons population has gone to zero? Then if eagle eats the pigeon, eagle will populate. Eagle population should increase. Who is eating the eagle? Hmm. Yes, exactly. So, yes, there is a cycle. There is a cycle. There is such a complex cycle. All are dynamical systems. If you observe all this, yes, food chain, it's also a dynamical system because you see when a lion eats a deer, right? If a lion eats a deer this year continuously, every day, lion eats deer, then deer population is going to zero. But they don't do it. It doesn't happen in that way. Okay. So that's a dynamical system. Why it doesn't happen? The answer is lying inside dynamical systems. So this is a complex dynamic system. Okay. Such systems you cannot understand just by your logic. Fine. So this is something computational. I want to show you that the plot you are seeing has been generated by Python, okay, from Python code. So you can see, this is just a simple equation. Xn plus 1 is Axn into 1 minus Xn, right? Simple equation. I mean, in your class 12th or class 8th, you might be knowing about this quadratic equation kind of thing. But if you start doing the Python simulations with it, you can see something very amazing. Yes. So my observation is what happens if I vary parameter A. Okay. If I vary parameter A on the x-axis, what you see? A. Parameter A is there on the x-axis. Yes. So when you vary parameter A, what happens to the system? Right? So what happens to the system when it is in between 0 to 1? It is same. It is constant, right? And you see only one dot. At each value of A, you see a single dot, isn't it? At each value of A, do you see single dot or double dot? Single dot. Okay. So that means only one population exists. Okay. After you increase the value of A, you see suddenly they double. Suddenly they double. Okay. That means two species are coexisting. Lion and deer are coexisting together. Okay. Lion and deer are coexisting together. And you increase further, four species exist together. You can see two has gone to four. If you zoom in more to that, 4 has gone to 8, 8 has gone to 16. And after that, you see this very huge band of black points. Okay, so that is unpredictability, which is where we are in right now. We are in an unpredictable world, actually. So we are in a chaotic world, to be honest. When what will happen, you don't know. Okay, so I mean, we are in that domain of chaos. Okay. Fine. So natural processes, what it has to do with natural processes. So natural processes have been decoded using scientific ideas and thoughts. Okay. So why aeroplane has been found out? Because of a bird flies, right? By seeing the bird, they have discovered the aeroplane. Yes. So many optimization algorithms in your machine learning, especially, can you name any? Adam optimizer. Suppose who doesn't know about it is fine, but you will in subsequent courses you will learn about Adam optimizer. It's a particular optimizer used in machine learning techniques. So how people have thought about that optimization processes? They saw the natural process. They saw the natural process. What can you give me some natural process of optimization? Ants. Anyone has seen ants? Very difficult nowadays to see them. But those who have old houses and those who eat sweets, okay, or spicy food, for them they will come. Okay. So ants come, but have you seen that ants take 10 times their load on their back? Yes, they take a small bit and even they carry a prey on their back and carry towards their home. Okay. How they do it? Okay. So all these are collective processes. Okay, fine. Anyway, So there still remain natural events which still need some answers, which are still not known to the community. Okay. Anyway, so I want to ask, many of you have seen lightning, right? Is lightning happening on a straight line? Why? Why? I think it's the simplest, the shortest distance to go from path A to path B is just by a straight line. So lightning wants to strike, right? Then go on a straight line. Why it has to go on a zigzag? Is that really a zigzag? That's the question. Is it really a zigzag? No, it's not really a zigzag. It has a geometry behind it, which many people are not aware of. Okay. So can we describe the geometry of lightning strikes? So that is also related to dynamical systems. Even trees. Like, have you seen trees have a structure? I mean, when you see trees, do you see that how the structure has been formed? From a seed, it grew, and then how he decided that it will branch, and every tree looks like the same. Every tree looks like almost similar, right? So why they look like it? Why? So my answer is there is a simple rule which the nature follows. Okay, and nature follows it again and again repetitively in a for loop. I think in your tomorrow class there will be programming session, so you will learn about for loops. Okay, for loops means you want to do the same thing again and again. Okay, same thing again and again. Okay, so nature does the same thing. Nature just adopts one technique, simple technique, and again repeats itself. Okay, that I will show you how to do it. Many of you have seen about snowflakes. Snowflakes. How many of you have seen Frozen? Frozen, a movie. Yeah. Okay. No. Oh, many. Good. So in that Frozen, you must have seen the geometry of that snowflakes. It's like hexagon kind of things. Okay. Fine. So here you see this. So you see the trees. Don't worry about the first figure. I will skip it. But see the B part. See the B part. So you can see that the tree exhibits such a striking geometrical behavior. And if I ask anyone to draw it, they will fail. Even if he's a brilliant guy, I will ask that you draw this tree. Then it will be very difficult for him, isn't it? So tree follows. I want to understand why tree is being seen like this. Okay, what is the geometry behind this? Basically, I want to ask. Okay, so it follows a simple rule. To be honest, I will reveal that rule. But basically, noted that it is a fractal. It's a fractal. I mean, take a small part, it will look like the bigger part. Zoom it, it will look like a bigger part. So we'll see what is the fractal. Okay, but anyway, so lightning strikes also, you can see they also occupy like a simple rule. Okay, simple rule. Fine. So you can see birds also. These are some natural events. So these we will see in videos actually. I will pause it and show you some videos. So birds, remember that you might have seen birds, they flock. They fly in flocks, right? They fly together. But uh, I mean, you can see this figure A. It is very terrifying. It is very terrifying. And it is just a scenario from a US city, okay, where you see not many people are there and they are free to do whatever they can do. Okay. So there are no apartments there, okay, buildings there, which can prevent them to fly like this. So they are doing free on a free will. Okay. So you can see they are collectively they are doing this structure. And it has a very beautiful structure, isn't it? So this is known as synchronization. Okay, this is known as a synchronization phenomenon. You must have seen this in aquatic animals also, like fish. Fish, they swarm, right? Fishes, they swarm, right? Together. How many of you have seen the video that a whale is coming? A whale is coming inside the ocean, right? You can see the whale is coming, and there are tiny, tiny fish. So the whale will target those tiny fish to eat. So as a community, what they do is all those tiny fishes they come together and they make a bigger size of those small fishes. And when the whale sees that formation, the whale kind of thinks that it's a bigger fish than me and slowly goes away. That did not even attack the tiny fishes. Have you seen those videos? No. Oh, maybe I like my area, so I only watch those videos. Anyway, um, So we'll see those videos, but just this slide you digest, then we'll watch some videos. So this brings us to a fractal. I mean, you note, see the table here in front of you, the table you are sitting in, it's a rectangle. The table you are sitting in is a rectangle, isn't it? Yes. Anywhere you are seeing, yes, the fan structure you can see is a circle. Yes. So all are very well known geometrical shapes. Yes. But if you see the lightning strikes or trees or all these things, they don't have a geometrical shape. Yes. So those are like fractals. Fine. Can you give me an example of a fractal which you see every now and then? Veins? Yes, exactly. Yes. Veins is a good example. Exactly a good example. uh, Veins is a very nice example because the veins, if you see, even your bronchioles, okay, in the lungs, the windpipes and those things, they are connected in a very nice network, and they are fractals. Even neurons, those are from bio AI, can comment better. Those who are studying, like neurons are, how many neurons are there in our brain? Anyone? Huh? Huh? Yes, millions of neurons. But those millions of neurons, they communicate with each other in such a way that if someone pinches you, you strike it, right? Collective 1 second response, less than 1 second even, right? So how you do that? I mean, neurons communicate, but how they communicate? Just like your birds, just like your fishes, okay, they also behave synchronously, right? Fine. So this brings me to something known as a fractal. Okay, fractal. What is a fractal? So fractal is a geometry actually. It's a geometrical shape which contains self-similar structures at infinite scales. What does it mean? More and more you zoom in the structure, it will look like the bigger part. More and more you zoom in the structure, it will look like the bigger part. And you actually eat that also. A fractal thing you eat. Can you give me an example? Can you give me an example of a vegetable which looks like a fractal? Huh? Exactly. Cauliflower. Okay, cauliflower or broccoli or whatever, they are a fractal. Why it is a fractal? You take a cauliflower, bigger cauliflower, okay, take a tiny part of it, okay, take a photo, zoom it and send it to a friend. Zoom it and send it to a friend. So the friend will say like how much per kg, right? Yes. So because they will feel that it is a bigger one. It's a bigger one. They won't notice that you have taken a small part of it. So the bigger part will look like the small part zoomed in. So those are like fractals. Okay, those are fractals. Now you can analyze why lightning strikes are also fractals. If you see a bigger lightning strike and take a small part of the lightning strike and zoom in, it will look like the bigger lightning strike. Okay. If you want, I can show the image A to you again. I mean, concentrate of any small part. This is the bigger picture. This is the bigger picture here. What you can do is take a small part of this. Take a small part of this and zoom in. Will it look like bigger part? Not exactly, but similar. Not exactly, but similar. I mean, lightning follows a kind of a pattern, branching pattern that is something like this. Okay. So same you see in the trees. Same you see in the trees also. And the part C, which you are seeing right now, is generated from the Python code. So it's a mathematical way to generate fractals. Okay. So I want to print this in my t-shirts actually. So this is a good idea I have. There are many good fractals which we generate, and I want them to be printed on t-shirts. So if you are getting this idea, this is a startup idea. Okay. If you are generating a startup, let me know. Involve me also in that. I should be a partner. Fine. Anyway, so many natural processes have been identified to have fractal geometry associated with them. So they are created by repeating a self similar process over and over in a feedback loop. Okay. One small exercise can I give to all of you? All of you. You must be tired since you had a morning big class, I think, and heavy food you had in lunch. I understand. But I want you to do this simple exercise in all of your notebooks. Okay. So you will get a feel of fractals. Okay. So notice that I will tell this rule. Okay. This is just like a puzzle. Okay. So I have a straight line. I have a straight line. Okay. This is a straight line. What I do with this straight line? Okay. What I do, I I cut it into three pieces. I cut it into three pieces. This piece and this piece, I don't disturb them. Okay. What I disturb is only the middle piece. how I disturb them, this transforms to something like this. Got the idea? How it transforms? This part is same as this part. This part is same as this part. But this part has been bent. Got the idea? Fine. Now what will happen to this part? Can you say? Now any straight line you see, you will do this shape. So how many straight line you see here? 1, 2, 3, 4. So what will happen to this guy? Yes. Then this one you have to do. Then this one you have to do. Yes. Are you able to understand this? Or do you want me to do on the board so that last people can see? Is it not visible properly? Shall I do it on the board, on the slides? Do on the slides, right? Okay. Mm. Okay. So what I wanted to you to do is this problem. So this is a straight line. Okay, this is a straight line. What I do, I craft into three pieces. So this piece I won't disturb, but this middle piece, I will break them into like this, like inverted V shape. Okay. So what this will transform to? This one. Now I want to iterate this process again and again. Okay. So what will happen to this space? You see this straight line. So what will happen to this? You will replace by this. What will happen to this guy? Yes. What will happen to this? What will happen to this guy? Yes. Can you go again? Okay. At some point, your patience will run out. Okay. Some point patience will run out, but after certain iterations, after certain number of iterations, it will look like something. It will look like something. It will look like the satellite boundaries of your coastal areas. Okay. Are you able to understand what I'm telling or no? Yeah. So this is like a fractal, generating a fractal. So you can apply Python codes to do this or any programming language. Since you don't want to do this manually, you can tell the computer to do this for you. Okay. So that's why programming is important. Okay. This is why programming is important. Just a motivation why programming is important to you. Anyway, so we will watch some videos before it. So let us see. Yes, let us start with a fractal generated by programming languages. So each frame in the video is an output of a programming language, and each frame is output of a programming language, and such frames have been combined to make a video. So this is a work of maybe around 1 week or 2 weeks. The 1 minute video which you are seeing right now. Are we ready? Shall we see? Okay. So this is just an example of a fractal. Okay. So you can see that we are zooming in, and zooming in means you are changing the x and y axis continuously. Okay. And see that you will see similar kind of patterns throughout. Okay. So this is a heat map. Actually, those who know about heat maps, just a heat map with colors. Each color represents a value. Okay. Each color represents a value. So what you are seeing is all values, but those values are color coded with colors. Okay. So you can see the same structure has appeared again, right? Which you started from. Fine. Yeah. So we can go again and again and again. So therefore I told you fractals are self-similar objects at infinite scales. Okay. The more and more you zoom in, the better and better pictures you start seeing. So yeah. But these are basic structures from where they evolve. So these are pretty interesting. I usually teach this in the class of Introduction to Computational Science, where I teach the Newton-Raphson method to compute the nonlinear or to solve the nonlinear equations. But I don't think I'll be taking computational science this semester. So I hope still you know about it. So this will go on forever. I mean, we have to stop it somewhere. Okay. But this is, I think, has anyone seen this before or no? Yes. Where? Who? Before? Physics. Oh. Who taught? Is it? Which subject you taught? You learned? Oh, yeah. It will come there. Hmm. Where is it? But these are, I will warn you that in your galaxy, you see similar kind of picture, isn't it? Yes, you see the spiral kind of structures. So, yeah, it has some relations. Anyway, so let us see uh, who are from Bio AI. You guys from Bio AI, right? So, you will be learning some chemistry also. Oh, yeah. Okay. Yeah. So don't like, yeah, my best aspect is my belief is I want to look at each and every student in my class, but somehow I get stuck with some students. Okay, so pardon me if I do that. And if you want to grab my attention, do something so that I can see. Okay. Anyway, so this is a chemical reaction. This is a chemical reaction which is a dynamical system. Okay, chemical reactions are dynamical systems, isn't it? Why? You put something else, and something happens. Right? So that is a chemical system. So I want you to see that you can actually see patterns or fractal kind of images in live chemical reactions. And this I would have admired that if it would have been taught in school. But I also came to know in my BSc MSc. So I did not have that opportunity to convey this to school children also. But anyway, we'll see this example. So this is an oscillating reaction, chemical reaction. All body processes are also chemical reactions and they are oscillating. So see this Petri dish. So the chemical reaction has already started. The chemical reaction has already started. And you see these patterns on a Petri dish. And it is not anything graphics. No video editing is done. It is live chemical reaction. Okay. So you see patterns. So these patterns you see are wave structures actually. This kind of wave structure you see when you sit near the pond and throw a stone onto the water and the water ripples start forming, right? So these you can see how these guys collide with each other. You see these guys are colliding with each other. This and this are colliding with each other. You see. So these are known as target waves. These are waves, okay, from chemical reactions. And believe me that your body reactions, body processes are also oscillatory reactions. Okay, all are oscillatory reactions. That means you have your reactions are not settling into a one particular chemical substance, right? It is oscillating in between two. Okay, so these are oscillatory reactions, and oscillatory reactions are dynamical systems. Okay. So this is one example. I thought of covering every branch, so that everyone will feel inclusive here. Okay. Shall we see this guy? The birds, I think. Yeah, this is a real video. Oh. I think that they do these structures only when humans are not around. Yes. I don't think there is a leader in this group. Everyone is doing their own job. I mean, the structure is really beautiful. I mean, we humans could never do this, I think. Yeah, this structure is beautiful. I mean, this is the best part, I think. Okay. So you could see these are known as swarms. So swarms of birds. And from here, by keeping into these factors into picture, they derive something known as swarm intelligence. I hope many of you might have heard this word, swarm intelligence, swarm optimization. Yes. If not, you can Google. If not, you can Google. Means by seeing these natural creatures, can we introduce something optimization in our fields? Can we optimize our work process? Okay, that's the motivation. So till date, you can see ant colony optimization. How many of you have seen an ant colony? Anyone have seen ant colony? Yes, you have seen in YouTube videos, is it? Like they put some iron, hot iron, right? Is that video? Cement, yes. And it goes and settles there, and after that they dig it out, and they found it out that it is a very complex structure. Yes. So how ants, just tiny creatures, have done that? So how they optimized their situation to create it, right? So this is ant colony optimization, which has been used in data analytics and your machine learning techniques. So in machine, so you might be confused, no? That I am talking about machine learning and I am also telling about optimization. So those who are feeling like machine learning, then for optimization, they will be saying, no, no, no. Right? Optimization feels more like math, but machine learning feels like a king, right? Machine learning. So, but to be honest, machine learning faces a loss. Okay, loss function. So that is like there is a ground truth and there is a prediction. So the ground truth occasionally is not equal to the prediction. So there is a error. So there, this difference between the ground truth and the prediction is known as a loss function. And your motivation is to optimize this loss function so that the loss function is minimum, so that your prediction gets high accuracy in machine learning, right? To do that, you need optimization techniques. You have to go to math. There is no other way. Okay. So we need optimization techniques and we need this ant colony optimization, swarm optimization. We need to see ants, we need to see real natural organisms apart from humans to build our efficient optimization techniques. Yeah. Same thing happened last year also. But this side, somewhere this side happened. Anyway, This I don't know which video it is. I don't want to play in public. I will play later and I will show you. So let us see this one. Yes, this is a good video of synchronization. Okay, let me pause it for now. And I want to ask you one question that is, wait a bit here. So you see this guy, like what you see on the bottom, you see two Coca-Cola cans. And on that, above it, there is a plank. Okay, like a wooden plank. Okay, and then what you do on that wooden plank, you have kept metronomes. These are known as metronomes, means oscillations. Like you can think of as a pendulum, just as a convenient pendulum. Okay. Now what he is doing in this experiment is one, two, three, four, five. Five metronomes or five oscillators are there. He will oscillate each one of them. Okay. So each one, since they are doing it for different time intervals, what will happen? If they are turning on the metronome at different time instant, what will happen? Can you predict the next second? Everyone will be different. Everyone will oscillate differently, right? But later, yes. But initially they will be different because everyone has been started differently, right? So what will happen after a few time instants? Yes, everyone will be in sync. So why everyone is in sync? That's a good question. Can anyone answer? Yeah. Did you had much food? Uh-huh. Yes, exactly. Correct, correct. Yeah, because of the can, like the wooden plank, everyone is at the same position. Everyone is at a common surface, right? Like no one is like in a disintegrate way. Like see this classroom, everyone is together in this classroom. I am also there. So the platform is the same. Now when someone, if someone there, like maybe if we put one Hulk there, okay, if there is a Hulk there and he smashes the foot there, right? Then this guy will feel the effect, right? Why he will feel the effect? Because this is a common platform. This is a common platform, right? If someone is a Hulk there and he smashes a foot there, will you hear it in the hostel? No, it won't be. I hope it won't be that much. Okay, but this is a fact. So it's a common platform that determines the behavior of all the metronomes. Okay, so we'll see this in practice actually. So I've taken this video from YouTube actually. Till now they are not together. They are not in sync yet. Why? Because this guy has not been synced yet. But now it is, you see. Okay. So this is just a tiny example of synchronization. Fine. Done, right? Done, done. Sound is okay. Fine. We'll stop. Or you want to listen more? Sound is pleasing. They are vibing also. You can make raps. Who are pro in that? Hip hop something, someone can start. I feel that that group somewhere, some is it someone? I think they are keeping themselves. Let it out. You can start. Huh? Don't know. Okay, fine. So now, how about the ghost? Anyone ghost? I don't know much about ghost, but I thought that many if you light a candle and do something, it will come. No. It won't come, right? So therefore, I kept some candle videos. So for our data analytics course, no ghost should come. Okay. So just an example. So what happens like a synchronization? I want to give you an example like where the synchronization can actually take place. I mean, for bio AI people, for bio AI should not be specific, but those who are studying biology subjects, you must be aware of neurological disorders. Now, why neurological disorders happen? It happens mostly, one of the possible reasons is two. One is topological scenario, another is neuron scenarios. Topological scenarios means the, the interconnection between neurons has not been in a proper way. I mean, in that way, like if something happens, your brain is not able to transmit a proper signal to respond to it. Okay. So therefore, it's a topological issue. That means your neurons are not connected in a proper way. Okay. So when you analyze the neuron structure, the firing of neurons, I won't don't go, want to go to specific nature, but I want to give an idea that all happens due to current. Even in our body, current flows because neuron they connect with each other because of the voltage difference. Okay, there is a voltage difference and there is a synapse due to which information flows from one neuron to another neuron. Neurons are not actually connected like we people hold hands. Neurons don't hold hands. Neurons are still not connected, but there is a chemical substance which makes them connect. That's like a synapse, right? So that doesn't happen in mentally challenged people. Okay, so this is a difference between a normal and a mentally retarded one. Okay, another aspect is topology. I told you, no? Topology and neurons. I told you. So therefore, synchronization is bit important topic. So when you fire these rockets and all, they all have to keep this in mind. Okay, so when one engine is separated out, second engine is separated out, they are all made in a plan. Okay, so therefore this is just a simple experiment. This is a simple experiment. What happens if you keep two candles side by side? What just a simple. So it's a fun activity to do. Yes. So here you see. What can you tell me about this video? Are they out of sync or in sync? How many of you are saying out of sync? How many of you are saying with in sync? In sync. In sync. That group is saying nothing. Huh? Don't. What is the issue? Now I identified that group. This we'll discuss in after the break a bit. Okay. So this is in sync. The candle is in sync. Okay. Now, what do you think? Will the candle always be in sync? Why then it is in sync? Can you give me an example where the candle won't be in sync? This is an example where candles are at sync. What can we do to make them not in sync? Yeah, maybe, yeah. But there is also an experiment here, antiphase. Why? Why you are laughing? What happened? Did you made any correlation or what? Which correlation? People are following us. I could not get need competition. Aspirants, they are following the same, but everybody following the same. But these two guys are not following. Okay. But anyway, I mean, this is a very nice example of not in sync. Not in sync. I mean, in natural scenarios, I meant to tell you that this phenomena is there. This phenomena is there in nature, and it is not just in your notebooks or in your Python codes. Okay, this is has some natural meaning to it. Now, after being out of sync, since they are too closer to each other, they remained in sync. you see, therefore they were parallelly occurring together. Okay, fine. So I think, is it a good time? I won't record this.